All right, guys, let's talk about some direct variations. Well, let's start with this concept here. The probability of someone watching you is directly proportional, which is the same thing as saying varies directly, with the stupidity of your actions. And so anyone who owns cats knows that that's a pretty typical cat activity. She's trying to find out if she fits in the container or eating what's in it. I don't know. Let's talk about direct variations. So when we say things vary directly or are directly proportional, what does that mean? All right, in a direct variation, as x increases, y increases by the same factor. And that's what it means to vary directly. Let's consider this example. Consider the standard shower head. A standard shower head puts out 3 gallons of water for each minute during a shower. 3 gallons for every minute during a shower. The amount of water used during a shower varies directly with the number of minutes the shower has been running. And when we talk about these situations, what we're saying is we say that y varies directly with x. Sometimes they say y varies directly as x. So that means that our y here has to be our amount of water used, and our x here has to be the number of minutes in the shower. So let's make a quick table of values that match this situation. So x is the minutes we're in the shower, and y is the gallons of water used. 0-minute shower uses 0 gallons of water. Well, duh, but that's going to be an important concept coming up with a direct variation, so I'm going to include that data point, that ordered pair. 1-minute shower, if you were capable of getting clean in a minute, would be 3 gallons of water. A 5-minute shower would be 15 gallons of water. A 10-minute shower would be 30 gallons of water. And then you lazy folk hanging out in that shower for 30 minutes, that's 90 gallons of water. Just for a second, let's think about what that means. There's a picture there. That image is 1 gallon of water. That's 1 gallon of water. That's a 3-minute shower. Picture 90 of those lined up along the floor of your bathroom. They wouldn't even fit probably, would they? Because most bathrooms aren't that big. 90 gallons of water. You wasteful people, you. Take shorter showers, please. Anyway, that's a direct variation. Y varies directly with x. And anytime you hear a phrase in a math problem where it tells you blah varies directly with blah, the first thing is the y, and the second thing is going to be represented by the x. All right, let's continue. All right, some definitions. 2 data sets vary directly if they are related by a constant ratio. That constant ratio has a name. It's called the constant of variation. A graph of the data sets of direct variations is A, it's linear, and B, it will always pass through the origin. Now, we saw that in our previous example. 0 minutes was 0 gallons of water. 0, 0 is an ordered pair that is on my direct variation. A direct variation can be described by an equation that's y equals k times x, or kx, where k represents that constant of variation. If you take that equation right there and you solve for k, and you solve that equation for k, well, if it starts out y equals kx, and we divide both sides by x to solve for k, we get y over x is equal to k, y over x. And if you look here, that's what this says. The ratio of y to x is equal to that constant of variation. That's what we're going to use right here, this ratio, this idea. That's what we're going to use to determine if a data set that we're given is a direct variation, if it shows a direct variation relationship. So to determine if 2 data sets have a direct variation, you compare those ratios. You can also graph them to make sure that they form a straight line that goes through the origin. So let's look at this particular example. So if you look at what we've done here, we have x's of 3, 5, and 8, and y's of 15, 25, and 40. And then right here, we have the ratio of y to x, and we have all 3 of those ratios, and all 3 of them are equal to 5 over 1, which is indeed a constant ratio. Once you know the value of that constant ratio, and 5 over 1 is just equal to 5, you can use that as k. And you can then plug in that 5 and make an equation. Y equals k times x, and k here is 5. So y equals 5x describes this information, and it describes this line that you see here on the graph. Okay, so in this case, they do show a direct variation, and we know because of that constant ratio. Let's try a couple more. If you're getting the hang of it, copy it, pause it, and try it. Otherwise, let's do these together. So we're going to start by taking these values in here. We're going to determine if there's a direct variation. If there is, we're going to identify the ratio, write it in the equation, and plot the points on the graph to see if it's to be able to see definitively whether or not it's linear. So let's start with this first one. Is it a constant ratio? Start by dividing. 8 divided by 1 is 8. 4 divided by 2 is 2. So no, it is not a constant ratio. If I continue, 2 divided by 4 is 1/2, and 1 divided by 8 is 1/8, so definitely not. So we don't need to write an equation because it wasn't true. Is the graph going to be linear? Let's find out. Let's actually graph the points. So if I go in and I graph these points, I'm going to have 1/8. I'm going to use purple. 1/8 is right here. Okay, nice big dots. 2/4 is right here. 4/2 is right here. Well, that's not linear. And then 8/1 is over here. Well, that makes kind of a funky looking graph. That makes this shape. That's actually something called an inverse variation. And as you might assume, that's your next video. Inverse variation. All right, but no, it's not linear. Okay, that's a no. That's an O. How about the next one? Okay, let's switch colors. All right, constant ratio. Well, don't compare 0 divided by 0 because that's never going to work. That's just undefined, but keep going. 20 divided by 2, that's 10. 30 divided by 3, that's 10. Notice I'm dividing y divided by x. That's the constant ratio I'm looking for. 50 divided by 5, that's also 10. Yes, constant ratio of 10. To write the equation, replace the k with the 10. Y equals kx, and our k is our constant ratio, 10. Is the graph linear? Okay, 220, 0, 0, 220, 3, 30, and 5, 50. Does that make a straight line? It indeed does. It indeed is linear, yes, as a direct variation will be. Okay, same idea, except we're not going to do any graphing. This time I definitely want you to pause it and try it on your own. You are finding out here whether or not these are direct variations. Use your ratio of y to x to tell if they're direct variations. Pause it and try for 1, 2, and 3, and then continue, and I'll set you up for 4, 5, and 6. Okay, so hopefully at this point you paused it. All right, -2 divided by 0 is undefined, so that's definitely not going to help me. 1 divided by 1 is 1. Okay, so this is my ratio, y divided by x here. That's what I'm finding. 4 divided by 2 is 2. These are clearly not equal. This is not a direct variation. So the answer for number 1 is no. There's a relationship there. We don't know what it is at the moment, but what it is not is a direct variation. Let's try the next one. Okay, for the next one, divide. 4 divided by 1, that's 4. 8 divided by 2, that's 4. 12 divided by 3, that's 4, and 16 divided by 4, that is 4. That is a constant ratio. Yes, this is a direct variation. And to be specific, I could write it with an equation, y equals 4 times x, because that constant ratio 4 replaces the k in the equation. Last one of these. Divide again. 4 divided by -2 is -2. 2 divided by -1 is -2. Remember, we can't use 0 for this ratio. And 2 divided by 1 is 2. Well, that's not the same. So no, not a direct variation. Again, I probably do know what this relationship is here, but it's what it is not. I know what it is not is a direct variation. Okay? Now for the equations, it's a little bit different. For the equations, I want you to solve for y. If you can solve for y and you get y equals k times x with nothing else hanging on here and your x is not doing anything else besides a number times x, then you know it's a direct variation. Solve for y in this first one. That means I have xy equals 3. I've got to get y by itself by dividing by x. That is not a direct variation. That is not k times x, it's k divided by x. And again, when we look at our next video, that's an inverse variation, which we'll talk about in the next video, but it is not a direct variation. How about the next one? How can I solve for y here? What can I do to the right-hand side of my equation that solves for y? I can multiply by 3. So 3x equals y, or y equals 3x. Oh, that's not an x. 3x. Yes, this is a direct variation. And then the last one, solve for y again, and this time that means subtracting 1. Y equals x minus 1. Well, that's a simple relationship. That's a simple relationship. As x gets bigger, y does get bigger. So that part of a direct variation we have. But what we don't have is it's not a number times x, it's a number plus x, or x minus a number. We could say that this is -1 plus x, so we could say a number plus x. That's not a direct variation, because it doesn't specifically fit this format with the y equals k times x part. Okay, let's put some stuff together here. Let's connect some things we've already learned. So a direct variation is a linear function. All of the characteristics of a function still apply. The x is still the input, is still the independent variable. The y is still the output, is still the dependent variable. The domain and range are still the sets of all the x and the y values. And here's a really cool thing, that constant of variation, that's the slope. You just learned about slope. That constant of variation is the slope, that number in front of x. So let's utilize that to graph a couple of these direct variations. So you can use a variety of methods here. Your graph does not have to be super exotic, so please do not think that you have to have graph paper in order to graph these. You can use your notebook paper. I'm going to split my coordinate plane up into x and y axes. Well, I'm going to do it nicely. I'm not going to do it all messy. Try that again. And I already know some things about direct variations here. What I know is I know they all go through 0, 0. So I'm going to color code these. I'm going to do the first one red. I'll do the second one blue. And I'll do the third one yellow, or yellow, depending on how you like to say it. So, a couple of different methods you can use. For this first one, let's use just plugging in a couple of numbers in our heads. So we can make a quick table of values here, x and y, for this one in red. We know that 0 will give me a 0. Let's do -1, which gives me -6. And let's do 1, which gives me 6. Let's graph it. We definitely have 0, 0. We have 1, 6. 1, 2, 3, 4, 5, 6. And we have -1, -6. 1, 2, 3, 4, 5, 6. And we have a line that indeed does connect those points, and there's our direct variation for y equals 6x. So one way is to make a table. Second way, I'm going to use slope, and I'm going to use my rise over run that I learned. I know this has to pass through the origin because it's a direct variation. I'm going to use this slope right here, 3/4, as rise over run. So I'm going to go from my 0, 0, from my origin, I'm going to go up 3 and right 4. And that right there is going to be the next point that I want, up 3 and over 4. Do it again. Go up 3 and over 4. And that's going to be the next point that I want right there. You can continue this pattern in the other direction as well. Instead of up and right, you can go down and left. And there's the next point that we want. And again, down and left. And there's the next point that we want. And there is our second direct variation. Now this third one has a decimal. That's kind of aggravating. So in this third one, maybe I want to go ahead and change that decimal to a fraction. Well, mixed number first. And then 9 halves, -9 halves. So this is the same thing as saying y equals -9 halves times x. We can go ahead and use that as slope as well. So down 9 over 2. Oh no. I picked one that just plain doesn't fit on my graph. So I guess we're kind of out of luck there. So you go ahead and graph that one since I picked something that doesn't fit, and we'll have to take a look at that graph together the next time you come to class. See you guys in class.